Hi, my name is Debbie, and this is my lab report for the fourth lab of Physics 2212, where we investigated circuits and capacitors. The goals of this lab were to predict the behavior of circuits containing resistors that were in series and also in parallel, use voltmeters and ammeters to measure the actual values of current and potential differences in these circuits, and examine the behavior of ohmic resistors and capacitors. And I did this virtually through the circuit construction kit. The main concepts that we utilized throughout this lab were the loop rule, which states that the total voltage around a loop or the entire trip around a circuit, the total change in voltage will be zero, and also the node rule, which states that any current going into a given node is equal to the total amount of current going out of that node. For the first part of this lab, I built the series circuit in the top right of your screen in the circuit construction kit. My job was to estimate what I believe the current would be read by both of the ammeters in this circuit. The total voltage over the circuit was 3 volts due to the two batteries, and then the total resistance due to both of the resistors was 147. And as we know that I is equal to V over R, I estimated that the current would be read the same in both of these ammeters as it was a series circuit, and it would both be equal to 0.02 amps. After reversing the connection to one of the ammeters, I noticed that it negated this reading, and so therefore the current was then read as negative 0.02 amps. When I replaced one of the ammeters with a voltmeter, the voltmeter still read 3 volts, which was due to the two batteries. However, the ammeter read 0 because it was essentially an open circuit. There was no longer current flowing through these ammeters. To answer the question, what should the sum of the individual potential differences be for the circuit, I utilized the loop rule and the knowledge of the loop rule to understand that it should all add up to 0. So when I measured the potential differences, as you can see on the right hand side of your screen, the most notable ones were A to B, which is negative 3 volts, C to D, which was equal to the current times the resistance, which was 0.96 volts, and E to F, which was current times resistance, which was 2 volts. And when you add those all up, they are very close to 0. And then this allowed me to plot the graph of potential versus position around the circuit. So as you can see from A to B, there's an increase in 3 volts. And so therefore, my potential differences would all then be negated, as it is taking the opposite path around the circuit that I took to calculate these. And so from C to D, it would then decrease by almost 1 volt, and then from E to F, decrease by 2 volts, as you can see as I plotted on the graph below. Continuing with the questions, we were asked what would happen if we replaced the voltmeter with an ammeter in parallel with the 100 ohm resistor. So essentially the current would increase. So now there are two paths that are formed by placing something in parallel, but the current is going to take the path of least resistance, and so therefore all of the current is going to be flowing through the path with only 47 ohms of resistance, and so the current would then be equal to 3 volts over 47 ohms, which is equal to approximately 0.06 amps, which is an increase from the previously read 0.02 amps. I also wanted to mention that we reversed these calculations in order to check our calculations, and we checked that the 47 ohm resistor, when measured using the calculated voltage from previous calculations of C to D and then E to F, as well as across the whole circuit, we received approximately the same resistance with only a slight amount of error, as you can see here. Part 2 of this lab asked us to investigate capacitors, and so we created a circuit with a capacitor, a bulb, and a battery. The bulb had a resistance of approximately 10 ohms, so we connected the battery to the bulb and the capacitor in series and then observed it over time. So after turning on the battery, we noticed that the light went from very bright to dim over time, and then once we disconnected the battery and connected the capacitor directly to the bulb in series, the light bulb again went from bright to dim over time. And this was due to the charging and then discharging of the capacitor. So like I said, the capacitor was charging and then it was discharging. So while the capacitor was charging, the current in the circuit was actually slowing over time until it eventually stopped when the capacitor was fully charged. And then again, when the battery was removed, the capacitor began to discharge and the current again began flowing, except in the opposite direction as before, and then slowed down until it stopped and the capacitor was fully discharged. You can see the time it took to charge the capacitor and discharge the capacitor from this portion of the lab when the bulb was of different resistance here. So you can see that it took more time to charge and discharge when there was a higher resistance across the circuit. In part 3 of the lab, I once again set up a circuit virtually with a battery, a capacitor, and a light bulb. I measured the voltage across the capacitor using a voltmeter, and then I set the capacitor to discharge and recorded approximately 20 seconds of voltage versus time data. So then I plotted this data on the plot, as you can see on the right, in order to calculate the time constant of the circuit. So the slope of this plot is actually equal to negative inverse of the time constant, and so therefore the time constant once calculated was approximately 6.8 seconds. This is actually higher than what we expected. We expected the time constant to be equal to the resistance times the capacitance, and this was 6 seconds, so our observed was higher than expected. Both of the final questions ask if we were doing this lab in real life, what would change? If we'd used an actual ammeter, it would have a small amount of resistance, whereas our virtual ammeter had none. And so our measurements and readings in real life would be slightly lower due to an increased resistance in our circuits. This is similar to the answer for the second question. If we used a real battery to charge a real capacitor with no resistor, all elements would still have some resistance, whereas we would not have experienced this in the virtual lab, and so the charging process would therefore be slowed down, as we saw that the charging of a capacitor took more time when there was a higher resistance across the circuit.